Welcome to Math355 Abstract Algebra. This is lecture 21. And so what I want to do today is talk a little bit about groups and number theory. And this will be both, pure mathematics as well as applications. We'll talk a little bit about some of the math that's used in cryptography. And so we are getting towards the end of the semester. And so what I want to do is I want to give you a little bit of a sense of where do things go. So when you're trying to decide what classes might you want to take next, here is a little bit of which classes use material from group theory. What can you use? So this will be more on the number theory side. Also, in addition to just math classes, it's nice to know that what we're doing actually has real-world applications. And so we talked about cryptography at the very beginning of the semester. And a lot of this was based on, we know how to do certain operations like multiplication very easily, but we don't know a good way to factor. And so can we somehow create a security system or a way to transmit information based on this? If anybody finds a fast way to factor, then all of a sudden everything we have is susceptible to those attacks. So there's a search for new methods. With the coming of the quantum computer, there's a lot of fear that a lot of the prime systems could be susceptible now. So the question is, can you find something new? Okay, oops. I just realized one of these dates has to be wrong. Let's see. Today's the 25th, I think. And that should have been the 23rd. Okay, so I will fix that. All right. So here's the problem you were supposed to think about. Given any large number n, are there infinitely many vectors in Rn such that any subset of n of them are linearly independent, but any subset of n plus one of them are linearly dependent? So part of this should be easy. Which part of this is easy? Yeah, the n plus one. So because we're living in n-dimensional space, as soon as I give you n plus one vectors, they have to be linearly dependent. So the second part is really no big deal. What about the first? Can you find infinitely many vectors so that no matter which n you take, they will always be linearly independent? And if so, can you do this in a constructive way? Any thoughts? So as a general rule in life, if something is hard, try to do something easier. Rather than finding infinitely many vectors such that any subset of size n are linearly independent, what would be an easier warm-up problem? Okay, so what specific case? How many should I find as the first possibility? Good. So one possibility is I could try to do, a small case of n. I could do maybe n equals 1, n equals 2, n equals 3, and try to build some intuition. So that's one way to go. And so that's a really good idea. If n equals 1, it becomes very easy. Anything you write down will work. If n equals 2, with a little bit of work, you might actually find something. So any thoughts about what might work for n equals 2? So maybe take the first vector to be 1, 1. What would be a good second vector? That will be linearly independent with 1, 1. You could do 0, 1. I'm going to just renormalize it so that my first component is still 1. So give me a second component that would work. Anything else? I'll do 1, 2. Now give me something that will be linearly independent with both of those. I don't want to be on the line 1, 1. I don't want to be on the line 1, 2. 1, 3. Dot, 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 1n, dot, dot, dot. Something like that would clearly work. So in the case n equals 2, I have something that's constructive and works. And then the question would be, can I take this and somehow bump this up in another dimension? Maybe I now put in some extra things down below. And the argument gets a little bit harder, but you could probably make this work. Another approach is to start off with n vectors that are linearly independent. So let's say we start off with v1, dot, 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 vn, and they're linearly independent. What is the volume of a line in three-dimensional space? 0. What's the volume of a plane in three-dimensional space? It's also 0. So the idea is, as long as I'm throwing away a finite number of lines and planes in three-dimensional space, almost everything survives. So if I look at what I have now, I have n minus 1. Let's assume these are linearly independent. Can you give me a way to ensure that they're linearly independent? Yeah, exactly. Maybe vk equals ek. So now I want to choose something that's linearly independent from any set of n minus 1 vectors. How many ways can I choose n minus 1 vectors from n vectors? But there's a better way of writing n as opposed to just n. It's a way that will generalize. I have n vectors. How many ways can I choose n minus 1 from these? The answer is n, but I want something that's going to generalize nicely. How could I interpret n? Well, but what am I going to do for the next level and the next level and the next level? Oh, but then once I have n plus 1 objects, I have to choose n minus 1 objects from n plus 1. Right. And so that's the way that's going to generalize better. So choose any v not in the choose n minus 1 hyperplanes spanned by n minus 1 of the vectors. And all we have to do is just choose something that's not in any of those. We have lots of choices. Let's call that vn plus 1. And now for the next one, how many do we have to avoid? Choose any v not in any of the n plus 1, choose n minus 1 hyperplanes. And that would be my vn plus 2. And we can just keep marching down like this. And at every stage, there's finitely many hyperplanes we're excluding. They all have 0 hypervolume in the n-dimensional space. So there will always be vectors that work. In fact, what this is telling you is almost any sequence of vectors you take will work. You would have to be extremely unlikely to choose something that lands in a plane or a hyperplane or a line that's spanned by lower dimensional sets. So almost everything will work. But this is non-constructive. I want to give you a constructive approach that's going to use some really good concepts that will be very valuable when we get to chapter 12. So I want to look at what's called Vandermonde matrices. And so they're going to be of the following form. 1, 1, 1, dot, 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 1. X naught, x1, x2, dot, 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 xm. X naught squared, x1 squared, x2 squared, dot, 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 xm squared. Again, depending on which book you look at, there's going to be slightly different ways of writing all of these down. And I'm going to keep going all the way down until I get to x naught to the m minus first power, x1 to the m minus first power, x2 to the m minus first power, all the way down to xm to the m minus first power. So do we all agree that this is a square matrix? It's m plus 1 by m plus 1. So I can calculate its determinant. What can you tell me about the determinant of this matrix? So who remembers the linear algebra? How do you calculate determinants? Oh, it's messy, but there's two phrases you can use. Give me a phrase. Well, what's a procedure that we can use to calculate the determinant? I need a formula. I need a procedure. You got to give me something. How do I find the determinant? You go to a mathematical. No. How do you find the determinant? Give me the phrase you use. Well, how do you find the determinant? There's a name for the procedure. Yes. Okay, and then what do you do? Okay, this is expansion by minus or cofactors, right? There's a name for it. We give things names. The other thing you could do is you could reduce the matrix. You could do Gaussian elimination and make it upper triangular, or if you want it to be different, lower triangular, and then read off the determinant by just going down the main diagonal. So we have ways to find the determinant. So you could do the expansion by minus, the cofactor approach. Painful. But what will you get at the end of the day? What kind of function will you get of the x's? Can you look at this and tell me what kind of function it will be? Will I get trig functions emerging? No. What kind of functions will it be? It's going to be polynomial. The determinant is a polynomial in the x's. So the whole point of today's lecture is you're not going to remember specific material, you're not going to remember specific names, as you have just demonstrated. But what I hope you will get from this is how do you attack a problem? How do we build up some intuition? Does everyone agree that if I asked you to find the determinant of this matrix right now, you would not be happy? We're going to do it in less than 2 pages by just looking at it. Right? Now, the way you expand by minus is you have to choose one element of each column and one element of each row. And there's n factorial ways to do this. So the number of terms grows rapidly with the size of the matrix. We will start to see a lot of this in chapter 12. So we have to choose something from the first row, something from the second, something from the third. So there are n factorial terms, such as maybe we have 1 times, maybe I have x3 times, maybe I have x4 squared, times maybe I have x0 cubed, times maybe I have x to the 8th, x sub 8 to the 4th, dot, 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 dot. And maybe the last one is going to be x7 to the m minus 1. Here's one of my possible terms. Does everyone agree that it's got to be something of that form? Something from the first column, something from the second, something from the third, something from the fourth. I have one thing from each column. What can you tell me about the degree? The degree of each term is going to be 0 plus 1 plus 2 plus dot 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 plus m minus 1. Right? If I add up all the different powers, it's going to be a polynomial. What's the degree of the polynomial? It's the sum of the powers. Do you remember the formula for the sum of the first integers? Yes, and so here n is equal to m minus 1. So if I write the sum in reverse order, then when we add, we get twice the sum is m minus 1 plus itself m times. So we get the sum is just m minus 1 times m over 2. So we know that it's a polynomial, and we even know the degree of the polynomial. We're making progress. We're trying to get some information about the shape of this. Okay, let's keep going. Can you give me any choices of the x's where you know the determinant will be 0? There's a really trivial choice which you can start with. Yeah, if you take them all to be 0, it's going to be 0. Great. What is the determinant 0? When 2 rows are the same, 2 columns are the same, when 1 row is in the linear span of several others. But let's start by trying to make 2 rows the same. Can you give me a way to make 2 rows the same? Make them all ones. So then everything would be 1. So one possibility is to make everything 1, but that's more than just making 2 rows the same. That's making every row the same. Yeah, if xi equals xj, then you're going to have 2 rows the same. So whenever, that's a terrible whenever xi equals xj, 2 rows are the same, so the determinant is 0. So thus the determinant, which is a function of my variables, has to be some function g of the variables, and then it has to vanish whenever an xi equals an xj. So I have to be able to write it as a product 0 less than equal to j less than I less than equal to m minus 1 of xi minus xj. Are we comfortable with that? That we know if ever an xi equals an xj, the determinant is 0. So when I take this polynomial, it has to be a multiple of xi minus xj. If I gave you a quadratic, can you factor any quadratic? Quadratic in just one variable. Do you know how to factor quadratic? Yes, what would you use? Remember, things have names. What would you use to factor quadratic? Yeah, quadratic, 3x squared minus 17x plus 24. What formula do you use to factor quadratic? And what's that called? Negative b plus minus square root of b squared minus 4ac over 2a. This is called the quadratic formula, right? If I give you a quadratic, you might be able to factor it by inspection. If I give you, x squared minus 5x plus 6, that's x minus 2 times x minus 3. But in general, if I don't see that, I can use the quadratic formula. I can get the 2 roots, and then I can look at x minus the first root times x minus the second root, multiply all that by a. We can factor quadratics without any trouble. This is a polynomial in m plus 1 variables, and I'm asking you to factor it. That's a much harder problem. But notice that just by looking at this, we were able to get some of the factorization done. We know that it has to have this factor, the product of xi minus xj. Now, what is the degree of this? So each term has degree 1, right? How many terms do I have? I have to choose 2 distinct indices between 0 and n minus 1. So I have to choose 2 numbers distinct from the set 0, 1, ... n minus 1. How many ways are there to choose 2 distinct numbers from that set? Okay, and which is? Well, you give me the formula for it.
It's 2
factorial. There's a nice formula.
Yeah, that's what I'm trying to do.
I know.
It's n factorial divided by 2 factorial times n minus 2 factorial.
Yes, but this is also a binomial coefficient. This is just M choose 2. I'm choosing 2 objects from M, and that reduces to M times M minus 1 over 2. And notice these are the same. We can't take I to be j, because if we took I to be j, we would get a 0 factor, and the determinant would always be 0. But we know that this polynomial is of degree m minus 1 times m over 2, and we know this product is of degree m times m minus 1 over 2. Well, multiplication is commutative. M times m minus 1 is the same as m minus 1 times m. What can you deduce about G? What must be true about G? Nope. Almost. What do you know about G? It's degree 0. So it is a so if it's degree 0, what do we know about it? No, it's constant.
Oh, right.
We don't know that it's equal to 1. It might be, and for extra credit, you will be asked to figure out what is that constant, due Tuesday. So let's look at this matrix a little bit more. It's not pasting. I'll try one more time. So let's look at this matrix while I try once again to copy it. The danger for us, we're trying to figure out what this is. What would be the worst value for us for that constant? What would be the worst value for us in terms of trying to... That's not going to paste. Never mind. We'll do it the hard way. What would be the worst value? Could be 0. That would be the worst thing for us. X0, X1, X2. Yeah, but then it's just the 0 polynomial. We're done, but then it's not an interesting object, right? If I have something that's identically 0, this is not that interesting. Yes, but so it turns out this is going to be very useful in Tuesday's class. And so I'm just rewriting the matrix because it doesn't want to copy. So here is the matrix. And we know that it is the determinant is some constant times the product 0 less than equal to j less than I less than equal to m minus 1 of xi minus xj. All we have to do is find one choice of the x's where we can evaluate this, and then we can get the constant. Okay? And what we're going to do is we're going to choose the xk so that the xm is going to be much, much larger than xm minus 1, which is going to be much, much, much larger than xm minus 2, much, 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 much larger than x1. I'm sorry, x naught. If we choose it like this, so that each variable is much, much larger than the previous, which do you think is going to be the term that contributes almost all of the value to the determinant? So we can look at a special case to just build up some intuition. 1, 1, 1. Let's say 10 to the 100. 10 to the 100 squared. 10 factorial to the 100 factorial. That's going to be much, much larger. And then we'd have, 10 factorial to the 100 factorial squared. 10 factorial to the 100 factorial. Take the factorial of that. And then just take that squared. So when you look at this, how many terms are there in the determinant? So how many terms would we have when we expand out the determinant? So this is a 3 by 3 matrix. How many terms are there when you expand by minors or use cofactors? There's 6 terms, right? which term do you think is going to be largest? It's going to be the main diagonal. So this is going to give the biggest contribution. By a huge amount. Each of these numbers is so much larger than the previous that when I look at the value of the largest one squared times the second largest to the first, it's going to just dwarf. And so what's the largest contribution I can get? It's when I just take down the main term. Is the determinant going to be 0? No. So we know the determinant is not identically 0 by looking at what happens in this extreme case. This is a really powerful perspective. You are all smart people. You're able to read books. You're able to pick up things. What's the value added in coming to a class at Williams and taking classes from professors? It's not for us to go through the arguments in the book. You can go through arguments in the book. It's to emphasize how do you think about things. And here we can look at extreme cases. So this is the value in extreme cases. And the determinant is not equal to 0. So C does not equal 0. And then extra credit due Tuesday, find C. So you're not allowed to look online. You're not allowed to talk to anyone other than your people in the class. Try to figure out what is the value of C. We've almost solved the problem. We've almost calculated the determinant. We know that it is some constant times this product. We know the constant is non-zero. For many things, that's all that we need. But we're so close, we might as well finish it off and figure out what is that constant. It turns out this also solves the original problem. The original problem was, can we find infinitely many vectors such that any set of n of them are linearly independent? By suggesting in class, we looked at the case n equals 2, and I knew where I wanted to go, so I was kind of tweaking how I wrote things. Is keep the first row always 1, or the first column always 1, and then just keep adding different numbers like this. If we look at these matrices, as long as my x's are all distinct, what can you say about the determinant? So it's non-zero. So basically, just keep choosing different values of x and have your new column, x. Well, I guess we're doing things here by adding rows, not columns. 1, x, x squared, x cubed, etc. If you keep adding rows like that, that will be independent of all the other rows. And so here is a constructive way to find infinitely many vectors where they are all linearly independent in subsets of size n. So there's a lot of really good stuff going on here. We have a complicated object, and to try to understand the object, we tried to look at some extreme cases. We tried to say, what can we say? Are there any cases we can understand? And we noticed that if 2 of the x's are the same, then the determinant has to be 0, so we know we have a factor. And we were very lucky that the number of factors was exactly the known degree of the determinant. So we're only off by a constant. And then we can lock down that constant if we can just evaluate it in one case. Okay, so what I want to do now is I want to talk a little bit about some applications of groups in number theory and in some industrial applications. So the textbook is by Joe Silverman, who has been a professor at Brown for a while. I was a postdoc, and he was kind enough when I was a postdoc to give me permission to use some of his elliptic curve images. So an elliptic curve for us is going to be something of the form y squared is x cubed plus ax plus b. Typically, a and b are going to be rational numbers, and we're looking for which values of x and y solve this. And there are many different constraints we could do. Maybe we want x and y to be integers. Maybe we want x and y to be rationals. Maybe we want them to be reals. Maybe we want them to be complex. Well, if we allow them to be complex, it's really not that hard. Y is just going to be plus or minus the square root of x cubed plus ax plus b. So you give me any x, and I can find a y. Let's say I restrict myself to real values. Will there always be a solution to y squared equals x cubed plus ax plus b? I'm going to choose a and b. And then no matter what x I choose, will there always be a y? Or what's the danger if you're trying to solve y squared?
Very definite.
Good.
The F field is the one for.
Good. So this is the mindset we had from just a moment ago when we were looking at van der Waals matrices. Look at extreme cases. No matter what a and b are, as x becomes large and positive, then the right-hand side is positive, and so there will be two square roots. But if x becomes large and negative, then no matter what a and b are, eventually it will overwhelm, and that's why the elliptic curve stops at some point. Beyond that critical value of x, there's never going to be a y that works because x cubed plus ax plus b will be negative. It turns out this is not the only way an elliptic curve could look. I could actually have an elliptic curve that looks something like this, where there's now three real roots. Is it possible, when I'm looking for x cubed plus ax plus b, is it possible that there's no real roots to that? So I look at x cubed plus ax plus b. Is it possible that that's never zero?
Oh, is it?
Well, x cubed plus ax plus b. This is a polynomial of odd degree. As x goes to plus infinity, it has to go to infinity. As x goes to negative infinity, it goes to minus infinity. So what result do we have from, say, calculus that helps us now? The intermediate value theorem. So by the intermediate value theorem, any polynomial of odd degree has a root. So we know there's at least one root. There could be three roots. Take a and b to be 0 or whatever. Is it possible that there's only two roots? Could you have two roots that are real and the third root being complex? So I see you shaking your head no. Why not?
There's like a little weird. So you just have like one imaginary thing you would sum them because.
Good. So you could actually expand this out and say, look, if I have two real roots, then I would have to factor it. If the third one wasn't real, when I expand it out, it's not going to be real. The other way you might remember is the theorem that if you have a polynomial with real coefficients, the roots occur in complex conjugate pairs. So if x is a root, if say r is a root, the complex conjugate of r is a root. So you can't have just one root that's not real. It would have to occur in complex conjugate pairs. Either of those is fine. It turns out that you can put a group on the set of rational pairs that satisfy the elliptic curve equation. So imagine P and Q are 2 points on the elliptic curve with rational coordinates. I can draw the line connecting them. And I look at that line, and that hits the elliptic curve in another point, and we'll call that point R. And if life was simple, we might say that that point R would be P plus Q. But it turns out we want P plus Q not to be there, but to be the reflected point down below. It turns out this makes addition on an elliptic curve work, and it gives you a group. So again, I can always define addition, but addition may not actually give me a group. This is going to give me a group. Now, if we have a group, what must be true? What are the 4 things that should be true for something to be a group? And this is a nice way to review the material from the class. Closure. What else? Identity. What else? Inverse. And associativity. It turns out associativity is the hardest to prove for all of this. The other ones aren't too bad. So what I want to do is I want to sketch the arguments here that there really is a group going on here. Okay? So closure, the first thing is we have to show if we take 2 points with rational coordinates and add them, then we get a new point with rational coordinates. So let's say we have P and Q with rational coordinates, and we want to show that the sum is rational. Now, what do you think is going on in the image on the right? We're adding a point to itself. How am I figuring out what line to draw? Imagine Q is getting closer and closer and closer to P. And the limit as Q approaches P, then P plus Q will go to P plus P. And as Q gets closer and closer and closer to P, instead of having the secant line, what do you get? The tangent. This is the tangent to the curve at P. And that's how you add P to itself. There is one point that might be a little bit problematic to add P to, because the whole point is we need to find another point of intersection on the curve. There's one point where it might be troublesome for P. So can you think of a place where it might be hard to add to P where it may not hit the curve again? Like over here? Is it? Well, if I do that, it will just hit the elliptic curve far down. It will hit again. There is one place. So can you think of a point that has some kind of interesting relationship with P? There's only one place. Any thoughts? So what do you mean by parallel? So parallel to the x-axis?
Yeah.
If I do parallel to the x-axis, I'm not allowed to add like that. It's not a tangent line. But if I were to do that, it would hit the curve in exactly 2 more points, right? So that would just give me either that or that. One of those would be my point Q, and I could still do the P plus Q. There's one place where if I try to put my Q there and I try to connect those 2 points, I'm not going to hit the elliptic curve again. Yeah, if I go straight down, if I put my point over here and I draw the line connecting them, where's my third point of intersection? You know, in every other one, P plus Q equaled R, and that reflects down to Q. Where's my third point of intersection? My third point of intersection is actually at infinity. And we consider that there is one additional point at infinity. It turns out this point down here is negative P. Because if P plus Q is coming down here to this red point, this point over here would be negative P plus Q. And when you add them, you would get that point at infinity. So not only is this helping us to figure out what to do in the case when the point is directly below, it's telling us in some sense, here is our point at infinity functioning as the identity element. And now if I take the point at infinity and just draw the straight line, it hits the curve down here at negative P. I then reflect and I get back up to P. So this procedure really does seem to be giving me a 0 element, the identity that we need. All right, let's now prove that we have closure. Okay, so closure. So we have y squared is x cubed plus ax plus b. A and b are rational. And we have points x1, y1, x2, y2 with rational coordinates on the elliptic curve. Okay. So if we think about what's going on, I'll draw the elliptic curve, like this with 3 zeros, something like this. So here's maybe my P, here's my Q, And then down here is going to be my, what I'll call my P plus Q. So I have some kind of line. So let's say the points on the line y equals mx plus beta. I can't use b because I'm using b as one of the coefficients of the elliptic curve. So we also have y1 equals mx1 plus beta, y2 equals mx2 plus beta. What do you think is true about the slope and the intercept? What kind of numbers do you think those are? Rational. So how would you prove it? Which one would you prove first? So you want to show that m and beta are rational. How could we do that? We've got two equations and two unknowns. I could write down matrices and try to solve them, but I think I can just do this by brute force. What should you do to the two equations? Which do you want to solve for first, m or beta? Nope. I think one of them is pretty straightforward to solve. Yeah, subtract. If I subtract, that's going to give me y1 minus y2 equals m x1 minus x2. So the slope is y1 minus y2 over x1 minus x2 if x1 is not x2. So as long as x1 is not x2, that's my slope. And this is clearly going to be rational because everything in sight is rational. All right, how would you then prove that beta is rational? Good. So beta is the difference of a rational and a product of rationals and is thus rational. So we know that the line has rational slope. So if we look at y squared is x cubed plus ax plus b and y equals mx plus beta. Look for things that solve both of these simultaneously. So this is then the same as mx plus beta squared is x cubed plus ax plus b, or x cubed, if I do the algebra correctly, minus m squared x squared plus a minus 2m beta x plus b equals 0. So this is the set of points that satisfy both the ellipse, both the elliptic curve and the line. Can you give me any roots of this cubic? Can you give me any points, any values of x that we know will work? I'm sorry? Well, I'm looking for just values of x. When I take x equals x1, that's going to satisfy the elliptic curve. It's going to satisfy the line. x1 is going to be a root of this cubic. Can you give me another root of this cubic? X2. So we know that this factors as x minus x1, x minus x2 times x minus, and we don't know much about it yet, x minus x3. And then everything that I'm underlining is rational. What must be true about x3? So which term do you look at to show that x3 has to be rational? I'm sorry? Well, unfortunately, we know B is rational.
Yes.
We know x1 and x2 are rational.
Yes.
That's not enough to prove that x3 is rational.
Yeah, but B equal to minus x1 times x2 times.
Yes.
Therefore, the product of x1, x2, and x3 must be rational.
Nope. So you have B equals x1, x2 with a minus sign, x3. We know this is rational. We know these are rational. That does not imply x3 is rational. Why does that not imply x3 is rational? X squared plus something x minus x1, x2, x3. I claim one of these terms is much easier to look at than the others. Which term do we want to look at to show that x3 is rational? The x cubed term, the x squared term, the x term, or the constant term? What do you think? The x squared. So we know that x1 plus x2 plus x plus x3 is rational, right? And since this is rational, that implies x3 is rational. So it's not a bad idea to try looking at the constant term x1. And the next level is in the field because part of it was already known and there's only one new thing that emerges. And we want to just keep controlling which new things emerge. So this shows closure. So it turns out there is a group. So we have a group on the set of rational solutions to y squared is x cubed plus ax plus b with a and b rational. And so the four things we have to show is closure, which we just did. We have to show identity. That's basically our point at infinity. Inverses. Use infinity. And then the last is associativity, which for the first time in our lives is actually hard. It is actually a little bit difficult to show p plus q plus r is the same as p plus q plus r. Now, if you truly love pages of tedious algebra, you can actually write down a formula for what are the coordinates of x3, y3 in terms of x1, y1, x2, and y2. You might have to be a little bit careful in case you have a situation where some of the points are the same. So you have to break it up into cases, and you can go through and you can just do the brute force calculation. There's advanced mathematics that helps. It is worth making one last remark. We just proved x3 is rational. What about y3? Is y3 rational? What do you think? What do we know about y3? It satisfies the elliptic curve equation. What else does y3 satisfy? So we're looking for the intersection of the elliptic curve with a line, and then y3 is going to be the negative of this, right? So what would be the y3 coordinate for the intersection? It's going to just be mx1 plus beta, which we now know is rational. Because we just showed x, I'm sorry, x3, not x1. I was just copying what was above, so. So because we know x3 is rational, because we know the line has rational coefficients, we know that y3 is rational. So its reflected value, negative y3, will also be rational. So this gives us closure. And again, we're reaching the end of the semester. I want to show you some special topics. I want to show you where does group theory play a role in other parts of mathematics. So part of this is to give you a sense of what's out there so that for the last lecture or two, we have a little bit of freedom in terms of if you want to know more about this stuff, we can talk a little bit more. All right, so what I want to do now is talk about one of the most important functions in all of mathematics, the Riemann zeta function. So it's initially defined as the sum over the integers of 1 over n to the s. And it turns out, using unique factorization and the geometric series formula, which just to quickly recall, geometric series formula. So if I give you 1 over 1 minus x, that's 1 minus x inverse, that's 1 plus x squared plus dot dot dot, if the absolute value of x is less than 1. So if I take this infinite product and just assume that I can do everything, that everything is justified, well, for each factor, 1 minus 1 over p to the s inverse, well, because the real part of s is greater than 1 over 1 over p to the s, that's going to be a number that's going to be less than 1. I can use the geometric series formula and expand each one of these factors out. And then when I have an infinite product like this, the only terms that survive are when I have only finitely many factors that are not ones. And if you want to see this, you could just imagine we only have 10 terms in the product, 100, 1,000, a million, and take the limit as you include more and more primes. And as I expand, because of unique factorization, you give me any integer n, and there's one and only one way of getting it by multiplying all the stuff through here. And so every integer can be written in this product, and everything in this product is distinct and is going to give us one of these integers. So these two expressions are the same. The reason this is so valuable is there is not much mystery in the integers. So this is 2024. Can anybody tell me what the next integer is after 2024? 2025, and the next integer after that, 2026. We even have an explicit formula for the nth integer. I can tell you explicitly what the nth integer is. We know what the spacings are between adjacent integers. We know how many integers there are less than a given amount. There's really not much mystery in the study of integers. The study of primes is much different. Anybody know the next prime after 2024? Yes, it is 2027, the next prime after that. It's actually 2029. We've got, in just a few years, we're going to have a twin prime pair coming up. It's very exciting. Much harder to find where the primes are. And the idea is we understand sums over integers. Maybe we can somehow use that to get information about sums of primes or properties of primes. The other thing is, whenever you see a product, what should you be thinking? So I want all of my students in all of my classes to get this. Whenever you see a product, what operation should you apply to that product? Do you know any operation that converts a product to a sum? Logarithms. You should do a logarithmic transform. And it turns out in complex analysis, taking the log of the zeta function is a great thing to do. because the log of a product becomes the sum of the logs. So why is this important? I'm going to require you to recall a little bit of your either calculus classes or multivariable calculus, depending on when you did sequences and series. You should have hopefully done P series. The sum of 1 over n to the P converges if P is greater than 1. It diverges if P is less than or equal to 1. This is a P series on the left-hand side for the zeta function. The difference is we're using the letter S and not P. Why aren't we using the letter P? P is prime, and we are not going to move P from prime to be the exponent. So we follow Riemann and we use S. It turns out to be very useful to define this for complex numbers and not just for real numbers. All right, so this is a P series. So if we take the limit as S goes to 1, this sum is going to diverge. If there were only finitely many primes, the product would have to converge. So this is a proof that there's infinitely many primes. So explicitly, we let pi of x count how many primes are there at most x. And by taking the limit as s goes to 1, we show that there have to be infinitely many primes. You might remember Euclid's argument. Look at the product of the first n primes and add 1. And that's either a new prime or divisible by a prime not on the list. Have you seen this argument? It's one of the oldest arguments still being used in mathematics. This gives you that there's at least log x primes up to x. The truth, and this is the prime number theorem, is that there's basically x over log x. So first order, that's how many primes there are. It's 0% in the limit. There's x numbers up to x. There's x over log x of them roughly that are prime. So in the limit, as x gets really large, the percentage of numbers that are prime is like 1 over log x. That's going to 0. But it's bigger than other sequences. How many numbers are perfect squares? Roughly how many numbers do you have less than x that are a square? 1, 4, 9, 16. How many would you get? So how many squares would you have less than x? About. So how many numbers do you have whose square will be less than x? Square root of x. So the fraction of numbers that are perfect squares would be root x over x or 1 over root x. How many numbers would you have that are perfect cubes less than x? X to the 1/3, you would have x to the 1/3 divided by x, or x to the negative 2/3. So even though there's 0% of primes, there's a lot more primes than squares. There's a lot more primes than cubes. So Euclid proves that there's at least log x primes up to x. You could investigate a little bit more this fact that the limit as s goes to 1 is infinity to get a better statement about how many primes there are less than x. I want to mention the second one to give you solace in case you ever feel like you do not belong in mathematics. I will share with you the worst result I have ever proven in my life. So it turns out, and there's a beautiful video about this, that zeta of 2, with the sum of 1 over n squared, is pi squared over 6. Very famous problem. Pi squared is an irrational number. If there were only finitely many primes, 1 minus 1 over p squared is rational. The reciprocal of a rational number is rational. A finite product of rationals is rational. So if there's only finitely many primes, pi squared would have to be a rational number. So because pi squared is irrational, there's infinitely many primes. And so I was curious when I was a postdoc at Brown, can I get any growth rate about how many primes there are up to x using the fact that pi squared is irrational? So we've talked a little bit about ways to quantify how irrational a number is. So I took one of those results and I was able to prove that there are at least log x primes up to x. So this seems bad because Euclid just multiply them all together and add 1, that gives you log x. I'm getting log x. It's even worse than that. The paper that I used that was talking about how you calculate the irrationality degree of this, do you know what results that needed to use? used the prime number theorem. There's x over log x primes up to x. So it calculated the irrationality exponent by using the prime number theorem that there's x over log x primes up to x. And using that there are x over log x primes up to x, I was able to prove that there's at least log x primes up to x. I dare you in your careers to ever prove anything worse than that. The reason I want to mention this is it's so easy to accidentally assume something. And again, before I did anything with it, I then opened up the paper and said, okay, well, what assumptions are they using in this? Oh, they're using the prime number theorem. Okay, I can't use this to then try to prove results towards the prime number theorem because I'm assuming what I'm trying. This happens all the time. I'm an editor at the Journal of Number Theory. We get people who have claimed to prove the Riemann hypothesis or other big results for Mars' last theorem, and they frequently assume a result that's conditional. Here is a paper assuming the Riemann hypothesis, we prove the following. Then they use that result to prove the Riemann hypothesis. You can't do that. So this is the life lesson. This is more valuable than doing another group calculation. Be very careful when you are pulling in results from another paper that you really check to see what are they assuming. And the paper I was using the prime number theorem. So I then actually opened up the proof, removed the use of the prime number theorem, and eventually I did get a non-trivial result. And so I eventually ended up getting a nice paper joint with some undergraduates on how quickly this has to go to infinity. All right. For the last unit for today, in terms of just some motivation for group theory and number theory, is I want to revisit one of our old friends. So M is going to be a prime number. And we're going to look at Z mod MZ star. So this is going to be all the numbers that are relatively prime to M. It turns out that this is a cyclic group. That's a non-trivial fact. So if I give you any number, if I give you M equals 7, 11, 13, as long as it's prime, Z mod MZ star is going to be cyclic. And one of the things we talked about early in the semester was group homomorphisms and finding ways to say, look, this group is equivalent to this group. Or I might have a kernel in my group homomorphism, so I might have to mod out by that. Here's a place where we're going to actually use all this stuff. Let's take e to the 2 pi I divided by m minus 1. This is called an m minus first root of unity. If I raise this to the m minus first power, I just get e to the 2 pi I, which is 1. If I square this and then raise it to the m minus first power, I would get e to the 4 pi I, which is 1. If I cube it, so all powers of this number, their m minus first power is going to be 1. It turns out that this can be viewed as a generator of a group that's equivalent to Z mod MZ star. Z mod MZ star, what are the elements of Z mod MZ star? What do they look like? Yeah, they're integers. E to the 2 pi I over m minus 1. That's not an integer. That's fine. It's an equivalence between the two. And so it turns out we can define what's called Dirichlet characters, which are extremely useful. There's two classes, and they're really the same, but I'll split them off. The first one is the principal character. Take any k that's relatively prime to m and set it equal to 1, and then all the k's that are multiples of m, set them equal to 0. What you can hopefully tell in what we're looking at here is that I only care about defining these characters on which residue class I'm in. If I'm looking at a clock with 11 hours, I don't care if I give you the number 3 or the number 14. They're the same on a clock with 11 hours, so I only care about defining my function on just the residue part. Let's think a little bit about the various structures that we have. So we call zeta m is going to be e to the 2 pi I divided by m minus 1. And we can look at 1 zeta m squared. How high do I have to go up to? What's the last one? M minus 1. As zeta m to the m minus 1. Oh, wait, no, zeta m to the m minus 1 equals 1. So I don't want to go up to m minus 1. How much do I want to go up to? M minus 2. And notice that gives me m minus 1 elements. So this is a cyclic group. So cyclic group, order m minus 1, and we have generator zeta m. It's possible, depending on what is going on, that maybe it has more than one generator, but we know zeta m is going to be a generator. So if we look at z mod mz star, so m is prime, and we're told that this is cyclic of order m minus 1, and here 1 zeta m squared dot 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 zeta m to the m minus 2 is cyclic of order m minus 1. We should have an isomorphism between these groups, right? So if this is cyclic, there's got to be some element G that generates it. Okay? So you give me any integer n in z mod mz star, then there exists an a, which can be a function of n, such that n is congruent to g to the a mod m. Because everything has to be a power of our generator. Yes? So you give me any number. So maybe m is 11, so I could give you 2, 3, 6, whatever. And that's got to be some power of g. So if you want, we can probably do a small case directly. Let's take m equals 7. So we're going to look at z mod 7 z star. So that's numbers 1, 2, 3, 4, 5, 6. Okay, what's 2 squared mod 7? Quickly. 4. 2 cubed. 1. So 2 is not going to be a generator. So G does not equal 2. Let's look at 3 squared. That is 2. 3 cubed is 2 times 3, which is 6. 3 to the 4th is 2 times 2, which is 4. 3 to the 5th is going to be 3 times 4, which is 12. Mod 7 is 5. 3 to the 6th. Uh, 6 times 6 is 36, which is going to be 1. And so 3 squared, 3. So I have found a generator. So 3 is a generator. And I can write z mod 7z star as it's generated by 3. And so it's 1, 3, 3 squared dot 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 3 to the 5th. Now I can make a little table. Here is my integer n, and here is my exponent a. If n equals 1, what power should I take for a? What's the power of the generator that's going to correspond to 1? 6, or I'd probably write it as 0. If I take n equals 2, what's the exponent that corresponds to 2? 2. And that's coming from 3 squared equals 2. If I take n equals 3, what power of 3 do I need to get 3? I get 1, yes, because that's the generator. I don't see it on the list because I didn't bother writing it. Yes. If I take 4, what power of 3 is going to give me 4? Yeah, 4. It's going to be 3 to the 4th is 4. And if I want 5, yeah, that's looking really kind of interesting. And so I've now found a way. You give me an integer n, and I can give you my exponent a. And my exponents are the numbers just 0, 1, 2, 3, 4, 5. So there's a nice correspondence between the integers in Z mod 7Z star and these exponents. What's nice about the exponents is I can just add them easily. And so it turns out we can actually define maps. So I have Z mod MZ star, and I want to map this to complex numbers of size 1, of absolute value 1. Well, this is a cyclic group. So all you have to do is, if you tell me what does it do to G, then what would chi of G to the A be if it's a group homomorphism? What would that have to be? So I have a group homomorphism. I raise G to the 8th power. What would chi of G to the A be? I bring the exponent outside. It would just be chi of G to the 8th power. So once I determine what my function is on the generator, I know it everywhere. And there's a good choice of A. What does chi of 1 have to equal? We have a group homomorphism. What does it have to do to the identity? This is a chance to review everything. Has to be the identity. So it's just 1. But I can also write 1 as G to the M minus 1. Chi is a function. So chi is a group homomorphism. So chi of G M minus 1, that's just chi of 1, but that's just chi of G to the M minus 1. So we have something which, when raised to the M minus first power, has to be 1. Therefore, chi of G is a M minus first root of unity, or chi of G is equal to e to the 2 pi I L divided by M minus 1 for some L in 0, 1, ... M minus 2. And so we're able to explicitly write down all the group homomorphisms here. And it turns out these are extremely useful in trying to answer a very famous question. If I give you two numbers, A and B, is there a prime congruent to A mod B? So for example, is there a prime P congruent to 3 mod 9? Yes or no? Can you find a prime congruent to 3 mod 9? Try again.
Oh, 3.
3, right? But it's only 3 is the only thing that works. Anything else, you'll have to be a multiple of 9 plus 3. Is there a prime P congruent to 4 mod 12? No. And what Dirichlet showed, if the GCD of A and B equals 1, then there exists a prime congruent to A mod B. And did this by showing for a given B to first order have the same number of primes for any A with GCD AB equals 1. So this is the alpha atomic gun approach to mathematics. I want to prove that there's one prime congruent to A mod B. The way Dirichlet did it is, not only did he prove that there's infinitely many, but he said that it's essentially the same infinity to first order for all the A's relatively prime to the same B. That the primes to first order fall evenly among the congruence classes where they could be. That's for centuries was the only way we could prove that there's even one. It's incredible overkill. The way we answer questions like this is these groups that we have over here and these group homomorphisms, these are what come into play. And again, this is a topic that we can explore more at the end of the term, but I want to give you a sense of why do we actually care about these group homomorphisms and these equivalences of groups and whatnot. It's to attack problems like this. All right, so this is a good place to stop for today.